All right, good morning. Oh man, come on. Good morning. Much better, thank you. So we're going to finish up 16.6 today, the second part of that, dealing with more parametric surfaces. Parametric surfaces are going to be the foundation of the next three sections that we'll be looking at in this course. And those three are, I guess you could say, the combination of everything we've been doing. And they can be a little bit tricky, but everything is based on stuff in this section. So get this surfaces thing right. The next three sections will not be too difficult. Okay, so a very quick review of what we did last time. Remember, a parametric surface equation is a vector equation with the parameters u and v, whose components are x, y, and z. And often u and v have some kind of bounds. And very often u and v can have geometric significance, but they don't. For example, in many of the examples we did last time, we let u and v simply be x and y. But that was mostly just for convenience. There's no reason why we have to attach any kind of geometric significance to u and v. And also remember that, well, let me sketch a picture first. Now imagine we got some kind of surface. Recall that if we hold u and v one at a time, we get these grid curves. And remember, grid curves are simply traces in some fashion. Traces, we're looking at slices of x, y, z. Now here, u and v may not have any kind of significance as far as geometry goes, so we call them grid curves, but essentially the same thing. So let's imagine that this green curve right here is a grid curve with, let's say, constant v. And let's say this other one right here is something we get when we set the grid curve with constant u. So there's some kind of curves on this surface. So today we're going to be figuring out how we can find a parametric surface area. And everything we need actually comes from the grid curve. All right, so let's assume that this grid curve, these two grid curves intersect at the point x, y, z. So let me sketch those things a little bit bigger here. Remember, this is our constant v. This is our constant u. And this point right here, x0, y0, z0, some kind of point. Now, if you look at the grid curve with a constant v, a vector that's tangent to that curve at this point looks like this. And this vector turns out to be partial derivative of our parametric equation R with respect to V. So this is a vector that we hold U constant. Sorry, this will be a U here, right? Because we're holding V constant. So holding V constant, allowing U to change. With a constant V, as U changes, we get this curve right here. And this other guy right here, same idea. This will be the partial derivative of the parametric equation, whatever it is, with U being held constant. So we allow V to change. So write this as RU, and this is RV. Okay, so these are two vectors that we can get just by simply taking the partial derivative of the parametric equation with respect to U and V. And we know that if I take the magnitude of RU cross with RV, then I'm going to get the area of a parallelogram that looks like this. Right? Remember, if you take these two vectors and you take the cross product and you take the magnitude, then you get the area of this tiny little patch. And this little thing will show up as a tiny little red patch on the big surface. So that's the idea here. We go to a point, we find RU, RV, cross them, take the magnitude, and then we repeat that for all of these points on the surface. And then put them all together, eventually we get the area of the entire surface. So we accumulate these little areas all over the surface. And of course, that means some kind of integration. And finally, we get the surface area of whole thing. Okay, does the basic idea make sense? Yeah? Okay, now with this in mind, we can write down the formula to calculate the surface area of any parametric surface, provided that you can take the derivatives, RU and RV, provided that you can cross them and take the magnitude. So basically, any surface that's smooth, any kind of surface we've been looking at that's smooth, we can always do this kind of thing. Therefore, the area of the entire surface is, call that A of S. That's what the book uses. We'll stick with that. It's a double integral over some kind of region D. We'll come back to that D in a little bit. The magnitude of RU cross RV. And then we do du dv. Of course, the order of integration depends on how we set up u and v. So this could also be dv du. So what this little d is, it's some kind of region. And what d is, this d is the domain of the parameters u and v. That's how we can calculate the surface area of any smooth surface that we parameterize using u and v. Also, by the way, the vector that is normal, meaning perpendicular, to the surface is just the cross product of Ru and Rv, right? If I just take the cross product, I get a surface, I get a normal vector that points either into the surface or away from the surface. If we're taking the area, it doesn't matter, but sometimes it matters a little bit. But anyway, we get Ru cross Rv. If you know that vector right here, then you can find the equation of the tangent plane. And we know the equation of a tangent plane. It's the normal vector dotted with some kind of vector in the plane equal to 0. Okay, so that part you've done before. It's not new. It's just now we got a little bit more variables to worry about. We got x, y, z. We got u and v. We got all these different things. So a little bit more complicated than what you've been doing, but not by too much. Okay, let's do examples. Let's start with a tangent plane here. Let's find the equation of the tangent plane. To the curve r of uv is equal to u squared plus 1, v cubed plus 1, and u plus v. Let's find the tangent plane equation at the point 5, 2, 3. Okay, so this 5.523, this is referring to xyz, of course. This is our point x0, y0, z0. That's one specific point. And this is the x component of the parametric equation, the y component of the parametric equation, and the z component of the parametric equation. So first thing you should notice right here is that we know x, y, z, but we don't know right away what u and v are at this specific x, y, z, right? But we can figure that out. Let's figure out what u and v are at x is equal to 5, y is equal to 2, and z is equal to 3. So like I said, we got more variables to juggle. We got a familiar x, y, z, the 3D coordinate system, and uv that are related to x, y, z depending on how the surface is parameterized. So we got two more variables to juggle here. But first thing first, let's figure out u and v. Okay? So we know that 5 is x. It is also equal to u squared plus 1. We know 2 is equal to y. It's also equal to v cubed plus 1. And 3 is equal to z, which is u plus v. In this case, seems like the y equation is the easiest one to solve. If 2 is equal to v cubed plus 1, that means v cubed is equal to 1, right? which means that v has no choice but to be equal to 1. Okay, so we know v. If we know v, then 3 is equal to u plus 1. That means u is equal to 2. Okay? So we're going to go back here and check. Is 5 equal to 2 squared plus 1? Well, of course, right? Yes. So basically what's going on here, you have what's called the overdetermined system. You have 3 equations with 2 things you don't know. One of these 3 equations end up being redundant as a check. So in this case, we solved the second and third one for u and v and used 1 to check. You could have used 1 to solve and then use one of the other ones to check. But you end up getting 2 variables with 3 equations. So you should always be able to solve. And as long as the equation the surface is parameterized correctly, then all 3 equations should agree. All right? Okay, so now we know what u and v are. We'll come back to that. Let's find the normal vector, which is Ru crossed with Rv, right? Ru is simple. We take the partial derivative of r with respect to u. So that's a 2u, 0, 1. And now we know what u and v are at this specific point that we care about. So we can fill in the u and v that we know. U is 2, right? So this is 4, 0, 1. Similarly, Rv, we take the partial derivative of r with respect to v. We get 0 in the I component, 3v squared in the j component, and 1 in the k component. And again, at the point that we care about, Rv turns out to be 0, 3v squared, v is 1. So that's a 3 in the middle, and 1 here. Okay? So crossing this is simple. Ru crossed with Rv. And we all know how to do that, so I'll just skip the intermediate process and just get to the normal vector. We get minus 3, minus 4, and 12. All right, now we got our normal vector here. Equation of the tangent line, tangent plane, sorry, is, remember, the x component of the normal vector times x minus 5, x0, right? And then the y component of the normal vector times y minus y0 plus the z component of the normal vector times z minus z0. And that's equal to 0. All right, so where do these numbers come from? Here, here, here. That's x0, y0, z0. So there we go. There's the equation of the tangent plane. And remember, we can use that to do a linear approximation near that surface. We've done that before, and near that point, the surface will behave very much like that, even though we don't really know what this looks like. And that's one of the advantages of using u and v. We basically stop caring about what this looks like. We can do all sorts of stuff with that without having to know exactly what that looks like. It might be a familiar surface, it may not be. And in this case, because we can do all this with RU and RV stuff, we kind of remove the geometric meaning once we come to U and V. Okay, so there's the equation. Questions on this example? All right, now let's do something with the surface area. Let's find the surface area of the plane x plus 2y plus 3z is equal to 1 in the first octant. Some kind of plane that this plane goes on forever, remember. So asking the surface area of a plane is a meaningless question because it's infinity. But if we trap that in the first octant, then we have a finite little region to talk about. So that has a fixed area. Okay, remember how to sketch this. You take the plane equation, you set two of these to be 0, 2 at a time. If y and z are 0, x is equal to 1. So that's the x-intercept. If x and z are 0, then 2y is equal to 1. So that's your y-intercept. And if x and y are 0, then 3z is equal to 1. So that's your z-intercept. And this infinite plane trapped in the portion of that infinite plane in the first quadrant end up being this triangle. We've seen this before. This is not a new situation. Now, in the past, we calculated the volume of the solid below that, right, with a double or triple integral. Here, we're going to actually be finding the area of that triangle. Okay, first thing first, parameterize the surface. And again, I'm going to let u arbitrarily be x and v arbitrarily be y. Remember, u and v, you can let them be just about anything you want. X and y are often easy choices in Cartesian, but sometimes you want to use r and theta in spherical, not spherical, in polar or other things. So you got a lot of freedom over this part of the process. And this means I can parameterize my plane, whose x component is always x, which is u, whose y component is y, or just v, and the z component I can solve from the plane equation. So it would be 1 minus x, which is u, minus 2y, which is 2v over 3. Okay, so I let x be u and v be y, and then z dependent upon the plane equation. You could have let u be z and v be y, and then let x depend on z and y. Like I said, you have a lot of freedom over this thing right here. Let's make a note of the domain of u and v. U and v in this particular case correspond to x and y. So let's look at the x and y plane. And on the xy plane, we see a triangle from 1/2 to 1, like that. So I see that u must go from 0 to 1. I can do a type 1 or type 2. Again, you have a lot of freedom here. I'll do a type 1. So u is going to go from 0 to 1. U really is x. And v is going to go from 0 to this line. V really is y. So this line would be 1/2 minus 1/2 x, which is u, right? Okay, so far so good? Yes? Now your head if yes, so I can see. Good, good, good. Now let's do our, where's the equation? Here's the equation. Remember, this is the area of a parallelogram formed by RU and RV near some point, and then double integral just moves that all over the surface. Okay, let's get our RU and RV. RU is equal to 1, 0, minus 1 over 3. And RV is 0, 1, minus 2 over 3. In the last example, notice RU and RV were dependent upon U and V. Now in here, why don't they depend on U and V? What's the reason why they don't depend on U and V? It's a plane, right? It's a plane, right? So if you take any two slices of that, it's always the same no matter where you are on that plane. It's perfectly flat in all directions. So of course they shouldn't. That means RU cross RV, the normal vector, should not depend on U and V at all. It's a plane. The floor is a plane. The normal vector is always up, no matter where we are, right? Same situation here. So that's why there's no dependency on U and V here. In general, they will, like in the last one, that's some kind of curved surface. Here we have a flat surface. Anyway, we can do RU cross RV pretty easily. Can I do RV cross RU? If I'm going to take the magnitude later, does it matter which way I cross? No. So RU cross RV or RV cross RU doesn't matter. Because remember, we're integrating the magnitude of that later. Let's just go U and V. And what do we get? We get minus 1/3, 2 over 3, and 1. All right, so the area, double integral over D of the magnitude of RU cross RV. And then in this case, we're going to have to do dV first because V is more complicated. It's a type 1 region. So you see, because of the magnitude here, it doesn't matter whether I do RU cross RV or RV cross RU. The magnitude will be the same. Okay, let's carry out that calculation here. U is going to go from 0 to 1. That's going to be the last integration we do. And V goes from 0 to 1/2 minus 1/2 U. And I'm integrating the magnitude of the normal vector. And it is, let's see, 1 over 9 plus 4 over 9 plus 1. I'm going to write 1 as 9 over 9. Right? So this is the magnitude of RU cross RV. The square root of the sum of the squares, that's the magnitude of any vector. And then we do dV first, du last. And now the easy part, this is, what is this thing? 14 over 9, so root 14 over 3, dV du. Take the constant out. First round of integration is just dV, so we gain a 1/2 minus 1/2 u, du last. And keep going. 1/2 u minus 1 over 4 u squared, 0, 1. 1/2 minus 1/4, that's 1/4. 1/4 times root 14 over 3 is root 14 over 12. And there we go. There's the surface area of that triangle. Okay? What do you think? Not so bad? We've done this before, right? You've done double integrals a ton of times. All we're doing is just a slightly different kind of double integral. So there's really nothing new here. Questions? Yeah. Say that again. What doesn't? The z component. Oh, because z is not independent of u and v. Just like in the xyz plane here, this plane is formed by a bunch of points. Once you've chosen x and y, once you've chosen any two of them, the third one depends on that equation. Here, same thing here. We restrict what we can choose for u and v, and the last component is dependent upon what we can pick out of the big pool of numbers for u and v. So z does have a domain, but it's implicit in the domains of u and v. Does that make sense? Good? Okay. Other questions about this? Okay, let's make this a little bit more interesting. Little bit more interesting. Let's find the surface area of the part of the plane that we just looked at, x plus 2y plus 3z is equal to 1, that lies inside the cylinder x squared plus y squared is equal to 3. Okay, so we got this plane that we just looked at that goes on forever, remember? And now we want to just find out the part of that plane that's inside a particular cylinder. Let me attempt to sketch what we got going on here. Let's start with a cylinder here. The cylinder, this is an infinite in the z direction, but cross sections of xy in the xy plane are circles of radius root 3, right? So something like this goes on up, goes on down, There's our cylinder, up and down. And now we're going to slice that with this plane that we just looked at. So it's going to slice through kind of a diagonal fashion like we saw last time. So here we go. There's our plane. Like that. What's the intersection? What is the shape of the intersection of these two things? Picture this in your mind here. Take a tube, any kind of circular tube, and you slice it diagonally. What do you get? Ellipse, right. Think of a banana or a stick of salami or whatever, lots of tube-shaped things. Slice it diagonally, you get a ellipse, right? So it's going to be some kind of ellipse that, man, that's going to be hard to sketch, but you get the idea. Intersection is an ellipse. That's not bad. I think that picture does the job. Does it? You get the idea? You can visualize this? All right, let's find out the surface area of that particular ellipse. Okay, same steps. We're going to start by parameterizing the surface that we're interested in. There are two things going on here. You're going to parameterize the one that we care about. We're looking for part of a plane, not the cylinder here. The cylinder forms the constraint. We're looking for part of the plane. So you're going to parameterize the surface whose part or whole that you care about, which in our case is the plane. And we can parameterize it exactly the same way we did last time. We'll let x be u, y be v. So the plane can be parameterized as r of uv equal to u, v, and removed it, but I can do it again. 1 minus u minus 2v over 3. Right? Now this time, what are the bounds of u and v? How do we figure that out? Geometrically, where can we pick u and v from? We got this plane that extends forever, but most of that plane we don't care about. So where can we, yeah. That's right, from on the ellipse, which is inside that cylinder, right? So we are constrained to pick u and v from inside the cylinder. So that's our constraint. And from that, we're going to figure out the bounds of u and v. So the cylinder lets us go anywhere up and down in the z direction as long as our u and v, which are x and y in this case, stay inside the cylinder. So cylinder is x squared plus y squared is equal to 3. which is equivalent to u squared plus v squared is equal to 3. That means on the x and y plane, which in this particular case coincide with the uv plane, but again, they don't have to, okay? Just because we let x be u doesn't mean that u and v always have to be u, x, and y, or even have any kind of geometric meaning. In general, they don't have to have any kind of meaning. We like them to have meanings so that we can at least get some sort of visualization, but they are not required to. So you see, v is going to go from -3 to, again, we can do a type 1 or type 2. Let's do type 1 again. So we see that u and v can be described by a type 1 region, letting u go between minus radical 3 and positive radical 3, and letting v be bounded below by the lower half of the circle, 3 minus u squared, and bounded above by the upper half of that circle, radical 3 minus u squared, the positive root. Okay? So now we've done enough of this. You all know that eventually we'll probably migrate to polar when we do the integration. But for now, we'll leave them as Cartesian. Let's get the rest of the stuff we need first. Namely, Ru, which we already did. What the heck is Ru? 1, 0, minus 1 over 3. Rv is 0, 1, minus 2 over 3. And we already did this last time. Ru cross Rv. If I remember, this turns out to be radical 14 over 3, right? It's the square root of 14 over 9, and we took the 3 out. So we did this in the last example. All right, so therefore, the surface area, which is that ellipse that we're interested in, is going to go from minus radical 3 to positive radical 3, negative root 3 minus u squared, positive root 3 minus u squared, radical 14 over 3, dv du. That's the integral we're supposed to solve. And now we know enough about different coordinate system. Let's migrate to polar, okay? Change to polar. So instead of u and v, we're going to do r and theta. We're talking about a circle of radius root 3. So r is obviously 0 to root 3. And theta is 0 to 2 pi. And now the key part to remember, whenever we change coordinate system, is that dv du, or du dv, in this case, is going to turn into r dr d theta. Okay, so 0 to 2 pi for theta, 0 to root 3 for r. We're integrating root 14 over 3 r dr d theta. Okay, so this should be pretty easy to do. What do we get? We get root 14 over 3, 0 to 2 pi. I get r squared over 2, 0 root 3 d theta. So that's going to be a 3 over 2. 3 over 2 times this stuff is 2, what is it? Root 14 over 2 times theta, which goes from 0 to 2 pi. So that's a root 14 times 2 pi, so that's a root 14 pi. So that's the surface area of that ellipse that we get when we slice through that tube diagonally. What do you think? Nothing new, really, right? Mechanically, nothing new here. It's just the difference is what you're integrating. One thing to note is that notice that we've changed stuff to u and v. And if you look at this double integral in u and v, this could be interpreted as a different kind of area, or maybe even a volume. So what this is going on behind the scene is that in x, y, z, we know what's going on. We have a good geometric feeling of it. But once it goes to u and v, it could lose all geometric meanings as far as we're concerned. So we could be calculating some kind of warped shape or some kind of warped volume in this UV space. That happens to have the equivalent number that will give us the surface area. But the UV space can have no geometric meaning whatsoever. And the shape that the ellipse in UV space could be something completely different. It's an entirely different space. All right? Okay, that's it for today. See you next time.